the physics of wind power. Now basically, a wind turbine is turning kinetic energy of the moving air into electricity. So let's look at how it does this. So the kinetic energy is the usual equation of half mv squared, where m is the mass of the air that you're running through your turbine. Now we can think of the air being run through the turbine. You just imagine the area swept out by the blades and look at all the air that's going to go through that area in 1 second. And that's going to form a cylinder. If the air is coming from this direction, everything in the cylinder's length is going to be velocity times the time. So for example, if it's 10 meters per second wind, then this will be 10 meters long, and all the air in the cylinder, 10 meters long and area A wide, will go through that swept area. So that's the theoretical amount of energy that's available to be harvested. So half mv squared, but what's the mass? It's going to be the density times the velocity times the area. Velocity times area gives you the volume of the cylinder. Factor this in, put that in place of the m up there, and you end up with the power from a wind turbine is a half times the density of air, velocity of air cubed, times the swept area. So let's look at this equation. So half rho v cubed a. Power is proportional to the cube of the wind speed. That means that wind speed is by far the most important thing. A high wind speed gives you an enormously more amount of power. This is partially because every cubic meter of air going past has more kinetic energy, but it's also because more cubic meters of air go past. So the amount of energy going through your swept area is very dependent on the velocity. It's also proportional to the swept area. Obviously a bigger wind turbine is going to let more air go past it, and so it's more energy available. So wind speed is critical to the economics of a site. If you're trying to pick a good site for a wind turbine, you want a large turbine to make A big, and you want to put it in a windy site, and you also want to make it tall because the wind is stronger at high altitude. All of this means that for wind turbines, it doesn't make sense to put one on everybody's roof. For solar power, you can have big solar plants or small ones. It doesn't really matter. The economics are not that different. But for wind, the economics are strongly in favour of big, massive, expensive wind turbines located at windy areas, whereas just putting a turbine on everyone's roof is, because of this v cubed and this a term, is not going to do you very much good. So this is quite different economics. That's why wind turbines have a very different structure from solar. Now let's try and work out what the practical efficiency of one of these things is. Because we've calculated the amount of energy available in all the wind that goes past, but how much of that actually turns into useful energy? I mean, bear in mind this area over here, only a small fraction of this is actually the rotor blades. Most of it's just in between the rotor blades. So let's put the equation in. Density of air is about 1.2 kilograms per cubic meter. Let's assume we have an 8 meter per second wind, which is fairly strong but not ridiculous, and a rotor blade of a diameter of 150 meters. Now what that means is you've got 17,000 square meters of area there, a lot of that. Density of air, mass of air, is rho UA, and that turns out to be 170 by 10 to the 3 kilograms per second. So what that means is it's 170 tons of air flowing through this area every second. You don't think air weighs much. It doesn't, only 1 kilogram per cubic meters, but there's a lot of cubic meters going through there, so 170 tons, that's like 15 cars, 150 cars or more of energy. And then factor in the power, multiply by velocity squared, that gives you 5.4 megawatts. 5.4 megawatts is the energy of all that wind pouring through that area. But in fact, a typical wind turbine will generate about 2.4 megawatts in this situation, this wind speed, this size. Which is actually pretty remarkable. The blades are only occupying a very small part of this area, but still it's getting about 45% of the wind's total energy. And as we'll see in a minute, that's about 75% of the theoretical maximum. So actually it's not just the wind that hits the blades, it's all the wind that goes through here. A good fraction of that power is being mopped up. And that's partially because the blades are rotating, so they'll get close to a lot of the wind. It's also because as the air curves around these things, it can push through even if it doesn't hit the blades. How does it generate so much power? Well, it's because it captures a lot of wind. As I said, it's about 170 tons of air passing through the turbine at a speed of 8 meters per second. That's about the same energy as 110 cars travelling at 30 kilometers per hour. And about 45% of that's turned into electricity, and then it repeats that every second all year. So that's how they generate so much power.